In recent years, humanity's focus has once again locked onto the moon, yet the objectives this time go far beyond the symbolic gestures of the Apollo era. Instead of simply proving we can get there, the aim now is to establish a lasting presence, build infrastructure, conduct in-depth science, and open the door to new industries that could change how we live on Earth and explore the wider solar system. Leading this modern lunar push is Firefly Aerospace, a US-based company that has already earned credibility in a notoriously unforgiving sector where the smallest miscalculation can spell disaster. Earlier this year, Firefly's Blue Ghost 1 mission achieved a textbook landing on the moon's Merecrisium, a relatively smooth northern hemisphere plane, but one that still required exact navigation, careful timing, and precise engineering to succeed. A reminder that easy landings on the moon are a myth, underscored by the fact that other American companies, including Intuitive Machines, have recently suffered failed South Pole attempts despite heavy investment and strong technical teams. The stakes are about to rise even higher as NASA prepares to send Firefly to a far more challenging destination, the moon's South Pole. This remote region is a labyrinth of deep, shadow-filled craters, knife-edged ridges, and terrain so rugged that sunlight rarely reaches into its depths, creating temperatures colder than Pluto and conditions that would destroy most hardware within minutes. Yet these same shadows may hold something so valuable it could redefine space travel. Water ice, trapped for billions of years in places where the sun's rays never touch. On the surface, the presence of water may sound like a survival bonus for astronauts, but its true value is strategic. Water can be split into hydrogen and oxygen, forming the propellants needed for powerful rocket engines, meaning that if enough ice is found and processed, the moon itself could serve as a fuel depot for missions heading to Mars, the asteroid belt, or even the outer planets, slashing costs and removing the need to launch all fuel from Earth. Finding, confirming, and characterizing those reserves, however, requires a combination of robust engineering and cutting-edge science, which is why Blue Ghost's South Pole mission will carry two highly specialized rovers. The first, Moon Ranger, developed by NASA's Ames Research Center with Carnegie Mellon University, is a small, suitcase-sized autonomous robot designed to operate independently in the moon's communications-challenged environment, where direct control from Earth is often impossible due to terrain-blocking line of sight and the multi-second signal delay. Moon Ranger will use stereo vision to create detailed 3D maps of its surroundings, plotting safe routes in real time without waiting for human instructions, a vital capability when operating near cliffs, boulders, and crater walls. The second rover, from the Canadian Space Agency, represents Canada's first major lunar hardware venture beyond its iconic Canadarm contributions to space shuttles and the ISS. This solar-powered but heavily battery-backed rover will be able to venture into the pitch-black interiors of permanently shadowed craters for up to an hour before returning to sunlight, a crucial advantage for sampling potential ice deposits. Its rugged design allows it to survive the extreme cold of the 14 Earth Day lunar night and resume operations when the sun returns, enabling repeated missions into darkness over multiple lunar cycles. Supporting the rovers will be Blue Ghost's onboard science payloads, turning the lander itself into a laboratory. This includes a laser ionization mass spectrometer, which will scoop up lunar regolith, vaporize it with a laser, and then analyze the resulting particles to determine their chemical composition at the atomic and isotopic level. NASA's stereo camera system for lunar plume surface studies, which will record exactly how rocket exhaust interacts with the moon's fine dust, a critical factor for designing future landing systems that minimize debris damage, and a laser retroreflector array that will allow scientists to bounce laser signals from Earth and pinpoint the lander's position with centimeter-level accuracy, aiding in both navigation and long-term geophysical studies. While the South Pole landing is slated for 2029, it is just one chapter in Firefly's broader multi-mission plan for the moon. Before that, Blue Ghost 2 will head to the far side of the moon, a hemisphere that remains hidden from Earth but is not actually dark, offering a uniquely quiet environment for radio astronomy thanks to the moon itself blocking Earth's interference. This mission will first deploy Europe's Lunar Pathfinder satellite into orbit, establishing new communications infrastructure, before landing to deliver the Lunar Surface Electromagnetics experiment, which will use this radio silence to capture faint cosmic signals from the universe's earliest epochs. Then, in 2028, Blue Ghost 3 will investigate the Gruithuysen domes, rare silica-rich volcanic formations whose origin is a mystery, since such lava typically forms in the presence of water and tectonic activity, neither of which are supposed to exist on the Moon. Solving this puzzle could force scientists to rethink lunar geology and the Moon's ancient history. Yet even as Firefly focuses on exploration, others are eyeing the Moon's commercial potential. U.S. startup Interloon has set its sights on harvesting helium-3, a rare isotope that could power next-generation fusion reactors for clean energy, improve quantum computing systems, and enhance medical imaging technologies. To locate deposits, Interloon will deploy a rover based on Astrolabe's Flex platform to hunt for titanium-rich minerals that often signal helium-3 presence, followed by a second rover in 2027 to collect and analyze samples. Already the company has secured purchase agreements. The U.S. Department of Energy has requested up to 3 liters of helium-3 by 2029, while a quantum computing firm has placed orders for thousands of liters annually starting the same year. Their mining technology reportedly consumes 10 times less power than current systems, enabling lighter, cheaper, and more mobile equipment, a key advantage for early lunar industry. With over $18 million already raised, Interloon may have a head start in what many are calling the lunar gold rush. If Firefly can demonstrate dependable, cost-effective lunar delivery and Interloon can prove the feasibility of resource extraction, the Moon could rapidly evolve from a symbolic destination to a functional hub for human activity, acting as both a scientific treasure trove and a springboard for deeper space exploration. The emerging lunar economy would be driven by a symbiosis of exploration and enterprise, science providing the justification and business providing the sustainability. In this new space race, the real victory will not belong to whoever arrives first, but to those who figure out how to stay, build, and thrive, turning our closest celestial neighbor into humanity's first permanent outpost beyond Earth. A permanent lunar hub could redefine humanity's relationship with space, serving not just as a remote research station, but as the foundation for a sustainable, multi-planetary civilization. In the near term, it would provide a low-gravity launch platform where rockets require a fraction of the fuel needed on Earth, enabling the assembly and refueling of massive spacecraft that could never be launched fully built from our planet's surface. This makes deep space missions to Mars, the asteroid belt, and even the outer planets not just technically possible, but economically viable. With confirmed water ice reserves, lunar facilities could produce both drinking water and breathable oxygen for crews, as well as hydrogen and oxygen propellants for ships, turning the Moon into a true interplanetary refueling station. The Moon's far side, shielded from Earth's radio chatter, could host radio telescopes capable of detecting signals from the universe's earliest moments, opening entirely new frontiers in astronomy. Extreme conditions near the lunar poles and in shadowed craters would provide the ultimate testing ground for habitats, power grids, autonomous robots, and life support systems designed for harsher worlds like Mars, ensuring technology is battle-tested before committing crews to multi-year missions. Economically, lunar mining of helium-3, rare metals, and other valuable resources could supply next-generation fusion reactors, advanced electronics, and medical imaging technologies back on Earth, potentially seeding trillion-dollar industries. A moon hub could also spark new forms of manufacturing in microgravity or vacuum environments, producing materials impossible to replicate on Earth. On the diplomatic stage, the cost and complexity of establishing and maintaining a lunar base would encourage international partnerships and shared governance, fostering a new era of global cooperation rather than competition. Over time, the Moon could evolve from a staging post into a thriving settlement with scientific laboratories, industrial zones, and even tourism facilities, acting as humanity's first permanent foothold beyond Earth and the stepping stone to the entire solar system.